All right. Well, welcome everybody to the Nationwide Eclipse Ballooning Project Speaker Series. I'm Susie Taylor. I'm based at Montana State University in Bozeman. I'm part of the education team for NEBP, and it has been my pleasure to be part of this speaker series. Thanks to the students who have been joining us week in and week out. Those of you who are watching the recording later on, it's great to have you. And today our speaker is Dr. Chris Packham from the University of Texas at San Antonio. We'll get started in just a moment, but I did want to say a quick thank you to the people who have funded the NEBP project. That's NASA's Science Mission Directorate and its SciAct program, as well as the NASA Space Grant College and Fellowship Program. We have students all over the country who are participating in scientific ballooning. I think we're just a little bit less than, or a little bit more than 1 month out from the next total solar eclipse. So I think everybody is on point and ready to roll. All right, so with that, I will turn it over to Dr. Packham, and thank you again for being here today.
Thank you so much. And you mentioned the eclipse. Do you get the total eclipse in your area?
We will not have totality in Montana, although I am planning to be with the MSU team in Fort Wayne, Indiana. So hopefully it's not cloudy.
Awesome.
I'm from the Midwest. I know what it's like in April. So we'll have fingers crossed for a good day.
So here in San Antonio, we do get the path of totality for about maybe a third of the city. So it's really gearing up here. You can see the eclipse glasses appearing in all the grocery stores, and just a general sense of it's coming. It's exciting. They're really, really thrilled to be part of this, and I'm spending a lot of time doing outreach and talking to folks, schools, etc., to get people excited. So, but this time I have the chance to talk to you folks at NEBP, and thank you very much for hosting me. It's a pleasure to be here. So again, my name's Chris Packham. I'm at University of Texas San Antonio. I also hold an affiliate position at somewhere called the NAOJ. That's the National Astronomical Observatory of Japan. And I'll say a little bit about that, as I was asked to talk a little bit about my own research and my story about how I got to here. So what I want to do is say right off the bat, these are my own opinions. These results and opinions may differ between persons and professors. I'm going to be talking to you about a little bit about what I think makes a good student and some tips for you as you go through your undergraduate or even graduate degrees. And I welcome pushback or discussion. Not everybody gets it right. I certainly don't get everything right. So I welcome your opinions there. So I'm a professor in physics and astronomy. I arrived to San Antonio about 12 years ago now. I got my PhD in London. Then I spent time in the UK, Japan, Spain, Florida, and now here in Texas. And I've been 3 times elected to be the secretary of the general faculty here at UTSA. So I've enjoyed moving around and enjoyed various opportunities that things have been. So I want to kick off with thinking about how to stand out as a student before I get into any astronomy stuff. So I've listed 5 things that I think are really important that I've seen as the students that I remember, or perhaps the students that I wish had been more connected to me. So the first is communicate with your professors. It's really important. Stay at the end, go and talk to them. Professors, yeah, I know we stand at the lectern or on Zoom and talk to students and present and lecture, but the real enjoyment is when you talk to a student and you can see them learning and they can get a really novel concept, etc. So interface with your professors. They may have opportunities that you may not recognize or may not advertise even, and only by talking to them and being a known quantity can you get to know that. Technology is so important. Make sure you know how to use cloud computing and iPhones or Androids or whatever, or the tablet stuff. Don't get complacent. Things change, they move fast, and that connects into digital fluency. It's really important. I know some folks that use shared drives and it's just second nature to them. Others, for some reason, just can't cope. And it's so hard working with people who begin to become digital influent. So make sure you keep those skills up. It's really, really crucial. There's a wide range of technology platforms in different classrooms. You've got to be aware of those and be able to use them and engage in discussion boards, etc. And then one of the things that I try to do in my classes a lot is working together as a team. Um, it's difficult. When you're a student, you're often doing individual work, but then when you get out into the real world, everything is done in teams, and that you become an expert in a small area of a grander project. Working together, communication skills, digital fluency, technology, etc., all these things, they're kind of like the soft skills, but I almost don't like the word, I don't like the idea of soft skills because they're foundational, they're fundamental. You've got to be able to work together in a team and communicate to people that maybe are just far outside of your own field of specialization. So these are all really important things, and I think help you to stand out as a student if you can really work on those topics. Communication with professors. This is a slide I'll show once in a while to my class just because it makes me laugh. Here is literally the slide. And so I've had previous semesters had interesting emails. They're not unusual. I'm just showing you a selection here. So ones that I like is Professor Packham, I forgot to do my homework. Can you extend it? Well, maybe I will. Dear Dr. Packham, could you help me? Oh, so great. Mr. Packham, well, you should really know the salutation of your professor. Packham, what's happening with? Well, not the most respectful way to start off, especially if you're asking for an extension to a homework. Yes, dear, I did register, was I think still one of my weirder ones. Or dude, where's HW1, THX? Well, no, it's just not good. And you can see, I honestly find it funny. It's just not appropriate if you're asking for an extension or trying to get something special. You've got to talk to people as professionals. So at least until you know your professor a little bit, then things can relax. But yeah, dude, where's HW1 was not made me laugh, made my other my other professors laugh, but yeah, wasn't quite the right way to approach me. All right, let's see. In the good old days, I'm going to skip past this one. How not to communicate well. So I always think it's easier to brainstorm in a negative way. So these are all negative ways. So how not to communicate well, or never chat in your class in person or Zoom because you might want to risk looking silly. Never participate in group work. You'll skate by on this one. Don't talk to your professor. Do the bare minimum to get through the course. Don't volunteer to help in the lab or events. Just better to wait. Don't get to know your class colleagues. It's also hard anyway. I still know some of my class colleagues, and I'm old. I still know a bunch of them. Don't go to we call it SI sessions, so restitution or additional sessions that are laid on by the university. I'll just get by here. Don't get involved in societies. Just wait until things are back to normal. No, all of these are not good ways to do this. So please invert all of these. So again, how not to communicate well, follow these paths. Please don't invert it. Get involved, get busy, get involved in societies, get to know your professors, get to know your colleagues. It really will help you enormously in the future. I can't overemphasize this. Communication with other students helps you in your immediate classes and can really help to build your long-term network. Again, I still know folks from my degree. I got my undergraduate degree in 1992, so that tells you how old I am. And a terrible thing with the pandemic is that we're all fractured and divided. So it's really important that we kind of reconnect in and connect in and talk to people. Societies and groups have a new importance in this current stage and indeed the future. So do get involved. I really urge you to do that and give back to the community. You have no idea where this can lead to. Especially on this increasingly online world. Get involved. I know you got a million homeworks to do, etc., but really get involved. It really, really can open doors that you never would have thought would be available to you or never even heard about. So please think about doing all these things. Technology, I'm just going to say again, just get used to it. Get used to Cloud Drive, iCloud, or whatever it is, Google Drive. Learn how to collaborate, get into good habits, work out the features that Zoom has. I still get people who can't find the mute button. Get used to it. We're all going to stay on Teams or WebEx or Zoom. Using this technology is really key to your success. Embrace it. For scientists, Python is the current language of choice. When in the old days, say 20 years ago, if someone had asked me how to become a good astronomer, I would have said, understand lots of physics, understand lots of math, and be a good student. I'll now add to that, learn how to do computer programming. Everything is leveraged off of computer simulations or computer approaches, and Python is absolutely the right one to go. As a final note, I think all of our actions have a carbon dioxide footprint. Online education work can really help to reduce this by an enormous fraction, up to 90%, if we factor in the increased network traffic and everybody having their laptops switched on. The reduction of driving around or flying around even more has an enormous thing. So this kind of online Zooming stuff, it's here to stay. All right. Digital fluency. This is one of my hobby horses. It's so crucial. Again, Python, if you want to stick around in science, especially. Although I was talking to a local grocery store manager here last night. Not just manager, chief technology officer. I should give him a much better title. Apparently, our local grocery store, their backbone is Python. And they use Python to do data mining and data visualization to understand what products to sell at which times of the year. Python really is becoming the language of choice as far as I can see. Make sure you're super comfortable in Word, Excel, and for me, PowerPoint and Adobe. We use Adobe here a lot at UTSA. Really, if you can't, you've got to be able to use those things and use them well. You've got to get great at using computers. It's a foundational thing. This area, Texas, for me is really interesting because of Tesla, Apple, SpaceX just down the road, and you know they assume you to be digital fluent. It's really a foundational thing. This last bullet point I like here: the space industry is going to be big. Well, I think I could almost begin to delete the word "going" here. I think it is already big and exciting. How exciting is it to think about going to space? All right, working together in STEM, just make sure you know how to work together. It really, really is important. I actually put this slide together during the pandemic. I said we're not going 100% back to normal. Well, I wouldn't be talking to you via this medium if we hadn't have gone through the pandemic and we all got incredibly used to sitting in front of a screen and dialing in to wherever it is that you guys, that you folks are located. It's just the way it is. And a comment and a tip my hat to NASA here. Diversity and inclusion is important now and will only increase in importance. The chance to do new cool things is so important. And if we want to harness the full potential of the city, the state, or the country, whichever way you want to, or indeed the world, we have to welcome diverse and inclusive opinions to harness the power of the intellect around us. And we've got to encourage that and embrace that. And so it's an exciting world, I think, that we're in right now. We just got to continue to push on this and overcome any barriers that get put in our way. My own representation, myself. So I do 3 types of things: research, black holes, instrumentation, and a little bit about exoplanets. Teaching, I teach all types of courses, or several types of courses, including one that I recently taught in a completely virtual reality world. All the students got VR goggles, and we had avatars discussing things around the table about the philosophy of space exploration. That was really cool. I'll see how much time I can talk about that during this presentation. And then service, I spent a lot of time working with my faculty colleagues here at UTSA. So showing an eclipse here as a great way to show things. Let me talk about the new frontiers of astronomy that I see. So telescopes are absolutely the fundamental tool of the astronomer. For astronomers, the bigger the telescope, the better. Galileo was the first person to use a ship's telescope to look at the sky. And here's a picture of Galileo on the right-hand side there. And this is absolutely true. The bigger the telescope, the better. But new electronic cameras can capture an enormous amount of light. It's less than 1% for the eye, 10% for photographic emulsion. New electronic cameras capture about 99% of all the light that falls on them. So big telescope, new electronics, that's really advancing astronomy at incredible rates. So they're the fundamental tool, and this is the type of typical telescope, the one that maybe Galileo used. You have like that ship's captain's thing. If you ever watched Pirates of the Caribbean, the one that Jack Sparrow used to use when he was sailing around. So those are the traditional ones. The bigger telescopes, we have mirrors that capture the light. This is better because those mirrors can be made much larger than the lenses, and we can use those mirrors to make really, really big telescopes. How big? Here's a picture of the National Science Foundation, the USA's flagship telescopes. This is the Gemini telescope, which is actually over in Hawaii. It's above the clouds. You can see that on the right-hand side, you can see the clouds below the observatory. Here's the telescope inside this structure. We can open it up to let the air pass through and allow it to cool down. This is what it looks inside the observatory. There's an 8-meter mirror, a mirror 24 feet across to capture the light from the distant objects that we want to go out and look at. These things are really cool. Here's a picture of a similar telescope. This one's over in the Canary Islands, Spain. This has a primary mirror 10.4 meters across, so even bigger than the one that's over in Gemini in Chile. So really, really cool type telescopes. I've had the opportunity to visit these telescopes and indeed build instruments to put on the back of these telescopes, and boy, what a pleasure it's been. Here's some images that I took looking down on the telescope, a whole series of other telescopes up on the mountain ridge there, looking down on the clouds, and just a beautiful sunset image here. It's a tremendous opportunity to enjoy this. It's hard work. You work 12-hour nights, 14-hour nights, and then get back down, have dinner, try to get some sleep at altitude, which is never easy. But what a phenomenal opportunity. How lucky I am that I get a chance to go to these wonderful places and peer galaxies to try to look at black holes or look at distant stars to try to look for those exoplanets around there. But still can't believe that I have the opportunity to do this, and I hope you folks may be inspired to follow and do some things like this. Let's talk about size. Telescopes went from 1 meter to 2 meter, 4 meter, then to 8 meters where we are. We're looking at future large telescopes, but let me just highlight, when we went from 1 to 2 meter telescopes, we found that numerous spiral nebula existed in the Milky Way. I'm showing what was the state of the art, which was basically a pencil drawing over here on the right side. When we had 4 meters, we found that actually these so-called spiral nebula are actually spiral galaxies, because we could observe, like this image in the top right, that they weren't nebula at all. They were galaxies at enormous distances and moving away at incredible speeds. So that transition from 2 to 4 meters changed our view of the universe. Before we had 4-meter telescopes, we thought there was only one galaxy in the universe, our own Milky Way galaxy. When we had 4 meters, humanity's view of itself fundamentally altered. With 8 meters, we found that there's a mysterious dark energy that's pushing the galaxies away. We still don't know what it is. It probably changes the fate of the universe. Ask me questions about that if you're interested at the very end. So it allows us, those 8 meters allow us to present an entirety of the history of the universe. Here it is. Here's the Big Bang, where my little fake laser pointer is. Then you can see there's a kind of clouds, in some respects clouds. It's not really, space is not opaque. We can't get light propagating through it very easily because there's so much stuff after the Big Bang. Then suddenly becomes clear. We start to see the first stars forming. These form the first galaxies, and then we have planets forming. And then, at least in a couple of places, well, at least one place that we know about, the Earth, life forms. It's really cool. One of the things that I always love to say is that we need stars and supernova stellar explosions to make the heavier elements, which often go to contribute the elements which our own human bodies are made up of. So it's absolutely true to say that all of humans have been through at least one supernova explosion. And as a famous astronomer, one of the people that inspired me into astronomy, said, Carl Sagan, we're all made of star stuff. That's just incredible. And one thing that I like Neil deGrasse Tyson saying, he extended that slightly. The atoms in my right hand come from a different supernova than the atoms in my left hand. Just incredible when we think about this. We've all been through a supernova explosion. So I think one of the most exciting things is to think about, are Earth-like planets rare or common? In 1995, not that long ago, I know it may sound like a long time ago to some of the younger students here, but for me, 1995, I still remember it well. No exoplanets known. Today, well over 5,000 exoplanets known. And we can even watch them in orbit. This image on the right-hand side, somehow the star has been magically removed using some advanced processing, and we can see these 3 planets directly orbiting around that star that's been digitally removed. When we use some advanced NASA telescopes, called the Kepler telescope, this estimates that the number of Earth-sized planets in the Milky Way galaxy numbers in the 17 billion. 17 billion Earth-sized planets in our galaxy alone. Wow, absolutely incredible. So here's a movie of those exoplanets in motion. You can see the exoplanets actually moving. An exoplanet is a planet that's in orbit around any star that's not the sun. You can see them moving. We can make movies now. Absolutely incredible that we have made such enormous technological strides. That's because we have 8-meter mirrors. We have incredible electronics that can collect all the light that falls on it. And now we have really pretty powerful computers that can do some of this digital processing to allow us to see far greater finesse. It's cool. Now, I'm going to skip past this to save a little bit of time. So it's really cool. But perhaps the most important question that we can begin to investigate right now is, how many civilizations do we think are out there? This guy behind is a guy called Drake. He made an equation, and he was a friend of Carl Sagan, actually. But he made an equation to say the number of civilizations with whom we can potentially communicate is just a very simple equation. The number of habitable planets in the galaxy, well, we know it's like 17 billion. The fraction of habitable planets with life, we don't know that answer. Maybe it's 0, maybe it's 1, or somewhere in between. We don't know. The fraction of life-bearing planets with civilization at some time. Well, you might have life, but we don't know if it's going to evolve to civilized life. We have no idea of this. And the fraction that are around now, you may have guessed it, we just don't know. So we don't know how many there are, but all that we do know is there's an enormous number of habitable planets. What we can say is as soon as the Earth was able to host life, life started on Earth. And the building blocks of life seem pretty common, pretty prevalent as we look out in the universe. So, particularly in our own galaxy. So maybe this is quite a high number too. Civilization, and now that's anyone's guess. That's one of the excitements. We need to drill down here and try to understand what's going on. So this is one of the cool things. Here's those numbers. We just don't know what some of these are. Okay, so the next generation 30-meter telescopes are really cool. I'm working with a bunch of folks from around the world to think about what we could do there. And one of the things that we want to do is look at these exoplanets. So let me see if I can get my animation to play. So one way that we can look at exoplanets is, if it's in orbit around the exoplanet, if we rotate that, we've got this exoplanet, it's going to move in front of the solar disk, the stellar disk here. You can see on the left-hand side, the amount of light that we receive gets slightly changed because of that planet moving in front of us. If we monitor it very carefully, we can get a good indication that there's a planet there by looking at the amount of light we get as time goes by. The other way we can do it is using something called the Doppler shift. We encounter the Doppler shift pretty much every day. If we hear a fire truck or emergency vehicle race past us, we hear the pitch of the siren change. That's because of the Doppler shift. The same thing happens with light. Same thing happens if we've got a planet, a very heavy planet, rotating around a star. Actually, the star gets tugged a little bit, gets moved by the gravity of that planet, gets pulled towards us or further away. The Doppler effect changes the color of the light that's coming out of that star. We can detect that tugging, and we can then infer the presence of a planet. We don't actually directly see it, but we can infer the presence of that. So that's one of the ways that we can, or those two of the primary ways that we can find the presence of exoplanets. It's pretty cool that we can do this. We can go one step further. If there's a planet going in front of the stellar disk or the solar disk, let's imagine it's got an atmosphere. A fraction of the light will be filtered through the atmosphere of that distant exoplanet. And then if we split the light up into its constituent colors, that's the way of taking spectroscopy. If we take the spectra as it goes through that atmosphere, we can look at the chemical elements. Each chemical element has a fingerprint that we can find using spectroscopy. So we can sniff out their atmospheres, and we can work out what materials are in the atmosphere. We can see if there's things like oxygen or ozone or other elements that might indicate the fingerprints of life. So this is really exciting. This is what a bunch of us are thinking about doing, and we're thinking about these big telescopes on the ground to be able to do this, the Giant Magellan Telescope and the 30-meter telescope that are still very much in the design phase right now. So I'm going to skip past this, and let me say I want to show a few JWST, the James Webb Space Telescope images. This has just been an incredible facility. I've really enjoyed using this, and let me say, why is it so cool? Well, here's like a scale image of the Hubble Space Telescope on the left, JWST on the right. Hubble Space Telescope is about the size of a school bus. That gives you an indication. Hubble has a mirror about 2.5 meters across. JWST has 6.5 meters across. So, of course, the area of the mirror tells you how much light it collects. So JWST collects 6 times or 7 times more light than the Hubble Space Telescope does. So that immediately tells you it can do new and novel things. But I actually don't really enjoy the question, which one is better? Because they're just different. Okay, JWST has a bigger mirror. That does give some real edge to it. But if I show here, Hubble looks at the visible part of the spectrum. JWST looks at the infrared part of the spectrum. So they operate complementary. They support each other. It's not one is better than the other. It depends what you want to do as to which type of telescope that you want to go out and use. So why infrared? Why do we use infrared technology for the James Webb Space Telescope? Well, here's I've got a picture of a ground-based application of infrared technology. Here I've got a first responder, and this firefighter is looking out for someone who is stranded in this fire. Of course, they're using visual wavelengths, and at this point, she won't be able to go out and rescue the person because she can't see through the smoke that's in that fire. If she switches to infrared, then humans glow at infrared, and that smoke, it doesn't become nearly as opaque at infrared wavelengths, and the firefighter will be able to go out and find that person, find that survivor. This is why they really use infrared technology. And which one is better? Well, depends what you want to do. In the fire, probably infrared is better, but you wouldn't want to do that when you go outside. You go back to visual. You just want to be able to switch around. Let me show some cute pictures here of some meerkats on the left at visual wavelengths, as well as a scary looking crocodile on the right hand side. Let's switch to infrared and see what they look like. Well, the meerkats are glowing. They're warm-blooded animals, whereas the crocodile is a cold-blooded animal, and so it's trying to soak up heat from the sun there. So you can see just the wavelengths that you look at tells you different things, and at infrared, you're kind of detecting heat. You can use infrared to say, I'm looking at heat instead of visual wavelengths. So with astronomy, astronomy is a kind of strange science in the sense that we can't do anything other than look at the objects. We can only look at them typically from one angle. In the solar system, yeah, we can land things there with a lot of effort, but if we look at these distant galaxies, for example, we can only look at it from one direction. We can't get there, at least right now, and so we can only look at them, and so astronomers like to use as many wavelengths as they can. You can see what this same object looks like from radio, infrared, optical, ultraviolet, and even into the X-rays. So that's the really cool thing. The current status is that we of the JWST is it's really cold. We want to keep it cold in order to prevent that heat, the heat kind of overwhelming the signal from those distant objects, those distant galaxies, distant exoplanets that we're going out to look at. The mirrors are effectively perfectly aligned. We align them to 1,000th of the thickness of a human hair, about 1 million miles from the Earth, using robotic technology. Isn't that cool? Just that we can do that. It still blows me away that this thing works. Here is the first image that was taken and released to the public. This is purely an alignment image. And to me, I love this image. I heard that this image was coming. Someone described that there's no longer sky. The sky is full of galaxies. So I think there's only one star in this image. That central star, this bright thing, is the only star here. Everything else you see is a galaxy. A galaxy is a collection of about 100 billion stars. So you can imagine just how many galaxies there are there. Here I'm showing the previous best image of this area. This is the same star. You just cannot see the level of galaxies. You can't see the quality there from the previous generation space telescope. So the progress that we saw from JWST was enormous. So let's go through just a few of these images. I'm going to show a few images and just run through them just because I love JWST images. Here's Jupiter, nearby object, of course. And here we can see the rings just highlighted here, and you can see one or two of the moons of Jupiter. But let's zoom in a little bit. Here's the disk of Jupiter. This thing's pretty famous, the Great Red Spot, a hurricane or cyclone that's been similar to a hurricane or cyclone that's been in the atmosphere of Jupiter for at least 400 years. Let's zoom in again. Looks beautiful, almost looks like the atmosphere is more like a liquid than it is really a gas. So just wonderful fidelity of images here that we can perform with the JWST. These images were some of this image was one of the first images released by the JWST. Here we're seeing a gas cloud where new stars are being formed, and they're slowly boiling away parts of the dust cloud. So these kind of blue streamers here is because the dust is being boiled away by these fresh new young stars. Within this dust cloud, in this kind of browny reddish area, without the JWST, we can't really see through that smoke, just like that firefighter when she was looking for the person on the floor, she couldn't see through. With the JWST, we can see through this cloud of gas and dust from which the stars are forming, and we can see stars that we previously hadn't been able to see before. What's even more incredible, who knows how many planets might be forming in those new stars that we see with this image. Just incredible to me. Beautiful image here of the Tarantula Nebula. Let's zoom in a little bit more. What's happening here is this central area is made up of many, many, many stars. And this starlight is melting, it's boiling away the inner region of this nebula from which this cluster of stars was formed, and we're able to see it with greater and greater clarity. We come back in a few million years with whatever version of JWST, we'll see that this gas cloud has been boiled back much further than it is right now. If we switch to the same area, we can see this at longer infrared wavelengths. We see it looks quite different, and this combination of looking at the kind of into the infrared and deep infrared allows astronomers to really understand and piece together how stars are forming in this area. It's just an incredible facility. Now, here is something called the Eagle Nebula. This is the three parts of the foot of the eagle, or the talons of the eagle. This is one of my favorite Hubble Space Telescope images ever taken. Let's take a look through the JWST. What an incredible image. Excuse me, what an incredible image to see there. Let's view them side by side. Which one is better? Well, you can have your own preference, but they're both beautiful. What we can see from the JWST is you can see straight through those gas clouds, far greater finesse, excuse me, and you can see far more stars in the JWST image than you can with the Hubble. Again, that's because you're able to see through that kind of dust clouds, smoke clouds, because of the abilities of JWST to use infrared technology. So I love this image. So let's continue to play around in this. So here we've got the Hubble. Let's spin it around to take as much space as we can on our screens here. And now let's fade it into the JWST. What an incredible transformation, and how we can use both images to understand in much greater detail what's going on in this area, which is there's hundreds of new stars being formed here, and hence perhaps the chance for new solar systems to form in this area. Here is a picture of the JWST using artificial intelligence to remove the stars. Really cool here. So now we've only got the nebula that we can see with the JWST. Finally, they released this image about a couple of weeks after the first image. Here's a deep infrared image of that nebula taken by the JWST. They released this just a couple of weeks after the infrared image from the JWST was imaged. Again, this is deep infrared. And it confused me why they were doing this. And just being silly, they released this, and it was very close to Halloween when they released this. And I noticed that if you zoom in, it looks like a spooky face looking at you here. So that must be why they released it in Halloween. I'm sure it's not NASA. I'm sure they didn't. They would just needed more time to process it. But it was very fortuitous that they released this spooky looking image over Halloween. Here's a wonderful image. This is called Stephan's Quintet. 5 galaxies, one of them has a supermassive black hole. So this is really what this image is called. But I think I'm going to say I'm lying to you. Why am I lying to you? Well, let's zoom in on just a portion of this image. Here you can see a galaxy, galaxy, galaxy. Everything except this thing, I think, is a galaxy. So when I say there's 5 galaxies in this image, no way. There is way more than 5 galaxies in this single image. There's 5 prominent galaxies, that's true, but most other things in this image is a galaxy. Remember, every galaxy is a collection of about 100 billion stars. What an incredible universe that we live in. Here's an image of the Cartwheel Galaxy. What happened here is there was a standard like spiral galaxy, but another galaxy fell through the center of the galaxy. It created a shock wave that moved out. That shock wave collapsed nebula into forming a starburst, a burst of star formation that we see moving out from the center. And that's what we see in this beautiful ring-type galaxy. We can look at this at both infrared and into the deep infrared, compare those images, and this is what we can see with the James Webb Space Telescope. What an incredible image. This is probably my favorite JWST image. This is called the Phantom Galaxy. And just looking into the very center of this galaxy, we can see what looks to be almost like a fractal pattern here. Here we see Hubble on the left, Webb on the right, and the fusion of them is what gives us the real beauty and the real scientific beauty. Connecting this data together is where we want to be in astronomy. And what a privileged time that we live in, that we have 2 incredible space-based facilities that allow us to make these incredible images. I'm going to show this one. There's again one of the first images here. There's a couple of stars here. These ones with like these spikes coming out, those are stars. Everything else is a galaxy. Again, everything else is a galaxy. And the thing that blows me away, the area of this image on the sky is equivalent to a grain of sand if you held it on the tip of your finger that's how much sky you'd be blocking out and representing this single image. What an incredible image this is. We can zoom in here and look at how the light from galaxies gets distorted because of bending of the space-time continuum. Ask me questions about that at the very end if you want to, and I'm more than happy to explain that. So I've gone through an enormous number of slides. I've ran through it, but I wanted to give you an idea of why I love being a professor, why I love astronomy, and my thoughts on how you can optimize your chances and move forwards and becoming a scientist or engineer, work for NASA or some other high-tech industries. So with that, I'm going to hand back. I know I went very, very fast, Susie, but hopefully not too fast. I welcome any questions or comments you folks might have.
No, that was amazing. Thank you, Dr. Packham. I was loving your slide about the different ways that people might email their professor. I have seen many of those and would love to share that with some of my colleagues. I think it's a really great reminder for our students. I really appreciated your tips on just being a good student and having that good relationship with your professor. Thank you for that.
Awesome.
Okay, so let's see if we have any questions from our audience. You are welcome to type something in the chat, or you can raise your hand and I'll call on you, or you can just unmute. We have a fairly small group today. Looks like Jamie Jacob has a question. Go ahead, Jamie.
Yeah. So I really love that. That was a great presentation, very inspiring.
Thank you.
And so I would love to see a more detailed version of this seminar. If you're ever interested in coming up, the ways to Oklahoma State University, would love to host you and have you give a seminar. Because that was really fascinating. I know we have a lot of students that are very passionate about this topic. So I love the images and the story that you told there. My background, I did a minor in astrophysics, but I'm an aerospace engineer. So while I love this stuff, I obviously tend towards the build it side rather than the science version of it. So I was wondering to get your thoughts about where do you see us going? Obviously, JWST has just been, transformational in terms of what we've been able to see. And I was on pins and needles when that launched. But what's next? What would you like to see next? And what's really the plan in the community? And I go back, I remember seeing a presentation probably around 2000, 2001, talking about Kepler and satellite hunting. And in my mind at that time, I was like, oh, this is not going to be possible. And just to see 2 decades later, that now we have confirmation of thousands of
Yes.
planets is just exciting.
Well, thank you so much. I appreciate the questions. And Jamie, feel free to email me. If you just Google my name at UTSA, you'll find me pretty easily. It's a fairly unusual name, so for at least UTSA. So feel free to contact me there. What's next? Well, a great question. I'm going to show a little video. I'll explain what's going on in this video. Here's the Hubble Space Telescope, which we're going to use for scale. NASA has commissioned a group of about 50 people from around the USA in academia, NASA, and industry to think about what is next. And what we're going to zoom by is that thing at the top of that movie is something called the Habitable Worlds Observatory. This is a telescope that's going to be similar in size to the JWST, but of course far larger than Hubble. It's effectively a super Hubble. And this will be NASA's first mission designed to understand if there's life on exoplanets that will be flying in space. So it's very much the successor in many respects to the technology that we've used from James Webb, but it will be at ultraviolet and optical wavelengths. So that's our next plan, to build that very large telescope, and again, to really go after the question of life on other planets. So we're just in that early stages now, Jamie. We've been at this for a year. You absolutely correct in thinking that we need to be planning the next thing.
So what has surprised you most about the JWST observations to date?
Let's see. I'm going to answer that in two ways. For my own research, we've got a bunch of JWST data, and the quality of the data has far surpassed what I could have dreamt of. Compared to what we can do from the ground in the infrared wavelengths, it is just absolutely incredible. What's most surprising, I think the results we're seeing from JWST are particularly exciting with regards to the Big Bang and the birth of galaxies and the birth of black holes. There's some significant tension now in the formation of galaxies and Big Bang models that we're having a lot of trouble to resolve. That's not my area of research, but it's a fascinating area. So I think that would be my dual way to answer that question, Jamie.
Yeah, it's not my area either. I'd love just to go to some of the AAS sessions just to see the discussions of this in real time, because I'm sure there are many diverse opinions now about, what appears to be a paradigm shift
Yeah.
Discovery.
Yeah, it's an exciting time. This is what you want when things don't work, don't behave
Exactly.
exactly as you expect.
Well, thank you so much.
Thank you, Jamie.
All right, we do have a few more minutes. If anybody else has a question, you can type in the chat. I'll take a look here, keep my eye on that, or just raise your hand or just unmute. I actually have a quick question while we're waiting. I was really intrigued by your virtual reality class. Can you tell us a little bit more about that? Were the students, it was students at your university, you were together, or they were virtual?
Well, it was all virtual. We all had VR headsets, and so we would discuss around the virtual table. And what we could do is use that new technology both for that discussion, but also I had a series of things in coursework that would use those VR goggles to gain a far more immersive environment. I was teaching this to non-science majors, and so initially people were concerned about the amount of money it costs for space exploration, but after going through things, really delighted to say that they became quite fans of space exploration. We discussed things such as who owns the moon, who owns Mars. We discussed about when will or if ever will artificial intelligence gain sentiency, and if so, what rights does it have? What rights do aliens have? Let's see. So we discussed a lot about the philosophy of science itself. How do we do science? So it was, literally a philosophy course. It was great fun to be exploring this domain, and it was, it was a lot of fun. I think the VR headsets, I don't know if you've had a chance to play around in some of them, but there's some incredible filmed, real filmed footage from the International Space Station. I have to say, I've seen movies, even IMAX stuff, where you've got the space station, and it looks just incredible. There's nothing like actually just being able to look around, tilt your head, look off into the blackness of space, look at the geometrical and the engineered nature of the ISS, and then turn down to look at the beauty of the Earth. Nothing like being an astronaut, I'm totally sure, but it's also far more immersive than just watching it on a flat screen. We really enjoyed it, really enjoyed it. And what it would be like on Mars, how things would look there. It's the simulations there are really cool. So it was a new way to teach. I'd love to do it again.
Yeah, that's amazing. And I love the topic, the philosophy of space exploration. Very cool. I believe one of our teams is actually doing something with the footage from the eclipse balloons and making that into a VR environment, which would be really awesome. So we'll let you know
Wonderful.
when that's
Please do.
ready.
I'd love to take a look.
Yeah, for sure. Okay, well, I'm just checking to see if anybody has any last questions. I knew you have a very busy day. I do typically ask our speakers, would it be okay if students reach out to you later if they have any questions? And if so, would you mind putting your email in the chat? Would that be the best way to reach out to you? Great.
Very good.
Awesome. And Dr. Packham, I have a webpage where I put the recordings. So if there are any links that you'd like to share for our students, you can just email those to me. You had a lot of really awesome links in your presentation. We'd be happy to share those out.
Wonderful.
And great. All right. Well, I want to say a huge thank you for being with us today. That was really amazing. I love seeing all the images. I really appreciate it. I wanted to say too, thank you for soft skills is a pet peeve of mine as well. I think you call them foundational skills or fundamental skills, which I greatly appreciate.
Awesome. Well, Susie, thank you so much. It's been a pleasure to talk with you, and good luck, everybody. It's going to be cool as we watch the future careers open up, and particularly space related.
Absolutely. Thank you again for being here, and have a great rest of the day.
Thank you so much.
Everyone.
I really enjoyed it.
Thank you, Jamie. You contact me on email. Thank you.
I'll be in touch.
Thank you, sir. Thanks. Bye-bye.